Hello, today we're going to do potentiometers and rheostats and potential dividers for A-level physics. Let us take a piece of conducting material in the shape of a wire. It has a cross-sectional area A, it has a length L, and it has a resistivity ρ, and you will know that the resistance of that piece of conducting material is equal to ρ times L divided by A. And let's just say that that comes to 10 ohms. Now we're going to put that in a circuit. So here is a 10 volt battery, and that is going to be in a circuit with the piece of conducting material that I just described, 10 ohm resistor, 10 ohms. And now I want to know what is the current that is flowing through that circuit. Well, we just take Ohm's law, V equals IR. That means that I is V over R, which is equal to the voltage is 10 volts, and the resistance is 10 ohms, and we get 1 amp. So far, so good, trivial. But suppose now I disconnect this end here. So there's now no longer a circuit, this has been disconnected. And I take this piece of wire here and I stick it halfway along the piece of conducting material. What now is the resistance, or the effective resistance? Well, the resistance is just simply this half of the wire, because that half is just dangling. The electricity is going, as it were, through here and then up the wire here. It's not venturing into here. So the resistance has changed. By how much? Well, we know that the resistance is ρL over A. Well, ρ hasn't changed and the cross-sectional area hasn't changed, but the length has halved. So if the length has halved, then the resistance has also halved. And so the effective resistance of this half here is 5 ohms, because the whole length was 10 ohms. So if I now want to know what the current is, well, the current, again, just as it was before, is V over R. The voltage hasn't changed, it's still 10 volts, but the resistance is now 5 ohms, and so we get 2 amps flowing in the current. And in principle, this is equivalent to this sort of setup where we might have a battery here. We're going to say that the voltage from the battery is Vs, the voltage of the source, and let's just have 5 2 ohm resistors in series. So each of these is 2 ohms, so the total resistance is 10 ohms, just as we had before. And if this is a 10 volt battery, once again we're going to have a current of 1 amp flowing in the wire. But if I were to again disconnect this wire here and bring it down instead and put it here, then of course you've now only got 4 ohms across the battery. These three resistors here are having no effect, they're just dangling, they're not connected to anything. The circuit is this, it goes around like this, through the 4 ohms, or the 2 lots of 2 ohms, and back up, or actually the current goes the other way around, doesn't it? Conventional current goes in this direction. And so now you would have that the current is V over R again, which will be 10 volts divided by now only 4 ohms, and that's going to give you 2.5 amps. But in this arrangement, you see you can only put the wire against here, or here, or here, or here, so you can have an effective resistance of 2 ohms, 4 ohms, 6 ohms, 8 ohms, or indeed 10 ohms. But under this arrangement here, you can slide this wire along the electrical conducting material continuously, and thus you can have any resistance you like from 10 ohms if you put the wire here, all the way down to 0 ohms if you put the wire right at the end of the resistor, in which case you've essentially got a short circuit because it doesn't go through the resistor at all. But you can have any resistance from 0 to 10 ohms, and that is called a rheostat. But it's worth noticing this, that no matter where you put the, as it were, the wire that you're touching against this resistor, the voltage across that resistor will always be the voltage of the battery. So the entire voltage of the battery is across whatever part of the resistor you choose to use by the placement of your wire here. So now I want to talk about a potential divider. We're going to have a similar sort of arrangement. We're going to have a battery, which is going to be our source voltage, and we're going to take that battery across two resistors in a complete circuit, R1 and R2. And I'm going to take two pieces of wire across here. I'm not connected them to anything at the moment. They're just essentially dangling pieces of wire. What can we say? Well, we can say that the Ohm's law, of course, always applies. V equals IR. So for the entire circuit, the voltage is Vs. The current which is flowing, which is I, and the total resistance in the circuit is R1 plus R2. And that means that the current is equal to Vs divided by R1 plus R2. Now suppose I take a voltmeter and I put the voltmeter across these two terminals here. In other words, I'm measuring the voltage drop across that resistance. What will that be? Let's call that VO, V output, as it were. Well, VO is going to be IR. And in this particular case, VO is going to be I, the current that we just calculated, which is Vs over R1 plus R2, times the resistance that we're going through, which of course is R1. And that means, if we just divide both sides by Vs, that VO divided by Vs, the output voltage, just to show you what I mean, the output voltage compared with the source voltage is going to be equal to R1 over R1 plus R2. And that is called a potential divider, because what you're essentially doing is dividing the potential of the battery into a smaller voltage. Let's, for example, suppose that both these resistances were 5 ohm resistors. So you've got a total of 10 ohms in the circuit, and let's suppose the battery is 10 volts. That means you've got a current of 1 amp flowing through the circuit. What is the voltage across here? Well, it's IR. The current is 1 amp. The resistance is 5 ohms. So V equals IR. The output would be 5 volts. So you could put a 5 volt bulb across here, light bulb, and it would shine. Whereas if you put the 5 volt light bulb across a voltage source of 10 volts, you'd probably break it. So this is a way of taking, if you've got a 10 volt battery but you want a 5 volt source, you can divide the voltage in this way so that you get 5 volts of output. It's called a potential divider. So let's just do a little test. Let us suppose that the source voltage is a 9 volt battery, and let us suppose that what I actually want is an output of 6 volts. Well, taking this arrangement here, you would say that V out is 6, V source is 9, so V0 over Vs is going to be 6 over 9, and that's going to equal R1 over R1 plus R2. 6 over 9, of course, just simply reduces to 2 over 3, and now we can just multiply both sides. We get 3 times R1 is equal to 2 times R1 plus 2 times R2, and that simply reduces to R1 equals 2 R2. So if R1 is twice the value of R2, then you will get 6 volts across R1 as your output voltage. It doesn't really matter what you use, so for example R1 could be 200 ohms and R2 could be 100 ohms, and that would achieve the output that you require. But in this arrangement, the potential divider, the output is strictly determined by the respective values of the two resistances. Suppose you want a variable voltage. Then you need to use what's called a potentiometer, and the potentiometer looks very similar. We take our source voltage, and now instead of putting resistances in, we take the piece of electronics that I devised right at the beginning, the conducting material, which you remembered had a resistance R equals rho L over A, and a current will flow, and we're going to put a wire here, and we're going to have another wire here, but this time it's a wire that we can move up and down this length here, so it can either go there or here, or frankly anywhere in between. You've got a slider, maybe a fader, and you can slide that fader up and down the length of this material here, and as you do so, the wire will connect at that particular point. And so now we've got VO, which is the output voltage here. And essentially what you can say is that wherever you put the wire, let's say we put the wire here, then this part of the resistance above the wire constitutes R1, and the bit below the wire constitutes R2. Just as you had in the potential divider here, R1 and R2 were fixed resistors. Now, the amount of resistance that is, as it were, part of the VO is R1, and the remainder is R2. If this is a 10 volt battery, and this is a 10 ohm resistor as it was before, then you can see that R1 plus R2 is always going to equal 10 ohms. So we can use exactly the same formula as we had before, and you can say that R1 over R1 plus R2 is going to be actually I need to go up a bit, don't I? R1 over R1 plus R2 is going to be the output voltage divided by the source voltage, but R1 and R2 is always going to be adding up to 10 because it's a constant resistance. And so, depending on what proportion of the source voltage you want, determines the amount by which you slide the fader up. If you want half of the source voltage as VO, then you need to go halfway along this cable. If you want just a quarter, you need to go a quarter of the way along. If you want 3/4, you need to go 3/4 of the way along. So the slider or the fader, which is carrying this wire up and down this component here, is determining the extent of the output voltage. It's a continuously variable amount, and that is called a potentiometer. So let's do an example. Let's take, on this occasion, we'll take a 9 volt battery, and we'll put it across our potentiometer, and that's going to be a 10 ohm potentiometer. So the resistance here will be 0, the resistance there will be 10. We take an output here, we take another output here, that's the output voltage, and this wire is capable of being connected anywhere along the potentiometer by a slider or a fader. And what we want to know is how far down the fader do we have to go if we want to achieve an output voltage of 4 volts. Well, again, we say that V out divided by V source is going to be R1 over R1 plus R2, which is going to be R1 over 10. But the resistance is directly proportional to the length. So if we assume that the length is also, say, 10 centimetres, then what we can say is that what we want is a length x over 10 centimetres, so VO over VS is equal to x over 10 centimetres. And if we want that to be 4 over 9, because 4 is the output voltage we want and the voltage source is 9, we'll get that 9x is equal to 40, and that gives you that x is 40 over 9, which I think is 4.4 centimetres. And this is therefore this slider here, this fader, which can achieve a variable voltage between 0 and 10 volts. In other words, well, sorry, here it would be 0 and 9. Between 0, if you put the wire here, you're not going to get any potential drop across that wire there. Whereas if you put the wire here, you're going to get the full 9 volts dropped across that, that resistor. You can go anywhere from 0 to 9 volts continuously. So for example, this could be a fader of a volume control on a mixing desk, on a sound desk. And the fader will simply give you a greater output voltage, and that greater output voltage determines the overall volume that is being sent to the speakers. That is flowing through that circuit. Well, we just take Ohm's law, V equals IR. That means that I is V over R, which is equal to the voltage is 10 volts and the resistance is 10 ohms, and we get 1 amp. So far, so good, trivial. But suppose now I disconnect this end here. So there's now no longer a circuit, this has been disconnected. Hello, today we're going to do potentiometers and rheostats and potential dividers for A-level physics. Let us take a piece of conducting material in the shape of a wire. It has a cross-sectional area A, it has a length L, and it has a resistivity rho, and you will know that the resistance of that piece of conducting material is equal to rho times it. And I take this piece of wire here and I stick it halfway along the piece of conducting material. What now is the resistance, or the effective resistance? Well, the resistance is just simply this half of the wire, because that half is just dangling. The electricity is going, as it were, through here and then up the wire here. It's not venturing into here. So the resistance has changed. By how much? Well, we know that the resistance is rho L over A. Well, rho hasn't changed and the cross-sectional area hasn't changed, but the length has halved. So if the length has halved, then the resistance has also halved. And so the effective resistance of this half here is 5 ohms, because the whole length was 10 ohms. So if I now want to know what the current is, well, the current, again, just as it was before, is V over R. The voltage hasn't changed, it's still 10 L divided by A. And let's just say that that comes to 10 ohms. Now we're going to put that in a circuit. So here is a 10 volt battery, and that is going to be in a circuit with the piece of conducting material that I just described, 10 ohm resistor, 10 ohms. And now I want to know what is the current